Hello class, welcome to the second lecture of Introduction to Material Science. This is atomic structure and interatomic bonding. This topic will include two different lectures. First we'll cover atomic structure and periodic table trends, and then the second will focus on chemical bonding or interatomic bonding and its influence on basic material properties. So I have several subtopics here. We are going to start with single atoms, go through subatomic structure, just a quick review of chemistry for that. We'll build up electrons within single atoms and review their energy levels and general probability distributions. Then we'll add on multiple atoms and look at how the electrons amongst multiple atoms rearrange themselves for a minimum energy configuration. That will lead us into bonding. Basically, that minimum energy rearrangement is effectively the basis of chemical bonding. Then we'll quantify that a little bit using Coulomb's law and using empirically derived relationships between attractive and repulsive forces between two atoms based on interatomic spacing. And then we'll go over trends of chemical bonding types and bonding energy on very important design-appropriate material properties. Okay, starting off with real fundamentals, atomic structure. As most of you know, atoms are composed of electrons, protons, and neutrons. These are all all particles that have real mass. Very small mass, but real, so it isn't just relativistic mass. And electrons have a mass that's about 4 orders of magnitude less than protons and neutrons. So the atomic number of any atom is equal to the number of protons in the nucleus, and because every atom, not ion, but atom, is charge balanced, it's electrically neutral, the number of protons has to equal the number of electrons. So weight of atoms goes by several different units. Generally, although we can express the weight of an atom in terms of the sum of the weights of all the electrons, protons, and neutrons in kilograms, adding them all up, it's very cumbersome to work with masses that are in the 10 to the minus 30th range. So there's a convenient mass unit that has been accepted, which is equal to 1/12 the mass of carbon-12, and that's known as an atomic mass unit. The atomic weight of any atom for any element is equal to the weight of 1 mole of those atoms, and that's 6.022 times 10 to the 23rd atoms per mole. That's Avogadro's number. For any of you who recognize that. So 1 atomic mass unit per atom is equivalent to 1 gram per mole. So when you read atomic weights off of a periodic table, you can use those numbers as a 1 gram, or a number of grams per mole of that atom, of that element, excuse me. If you wanted to get the weight in grams per atom, individual atom, you would just divide by Avogadro's number. So carbon, for instance, is 12.011 grams per mole. Hydrogen is 1.008 grams per mole. And you will use this later on when you're looking at building up density based on a number of atoms per unit volume, say in a crystal lattice, and then you want to know what the weight per unit volume is. You'll multiply by atomic weight. Okay. Electronic structure. It is effectively the electronic structure of atoms that determines a lot of the properties and also determines the ability of that particular atom or element to bond and what kind of bonds it'll have. And so to understand this, we have to kind of go back to our basic physics and remember that electrons behave both as waves and particles. And from our standpoint, the characteristics of electrons in an atom that are important are coming from its wave-like nature. And there's 2 wave-like characteristics that are really important to us. First is that electron locations are defined not by discrete points, but by a probability distribution. So there's, if you look down to the lower left, under s orbitals, they're shaped like a sphere. So that means there is an equal probability that you will encounter the charge equal to 1 electron in a distribution that's shaped like a sphere at a certain distance from the nucleus. P orbitals are dumbbells. So right at the nucleus, 0 probability of encountering an electron. Pretty obvious, right? You never see them right in the nucleus. But Too far away? No. And in every orthogonal direction you have effectively the same probability, and d orbital's about the same. So that probability distribution, which is effectively you can think of as a charge shape around the nucleus, is also called an orbital. And it's very important to think about this as a charge distribution versus a point charge. We'll look at point charges when we zoom out and we look at ions, or if we look at an electron as a point charge and try to envision the force of attraction or repulsion on it by a larger charge somewhere else. But when we're talking about orbitals and electronic structure, think about charge distribution. So the next wave-like characteristic of electrons that's important for our electronic structure of an atom is discretization of energy levels. Electrons can't exist at any location versus the nucleus, or at any location versus each other. This comes out of quantum theory. Electrons or the charge distribution can only exist in discrete steps of energy. Now in this case, energy is all electrostatic. So electrons, if you want to think about it based on Coulombic attraction repulsion, are going to generally want to be as close as possible to the nucleus, because the nucleus is positively charged and they're negatively charged, but simultaneously they want to be as far as possible from each other. So that combination of attraction and repulsion leads to this kind of discretization of energy. And furthermore, there's also a very high repulsive charge as you get very close to the core and the nucleus that we'll look at when we look at equilibrium interatomic distances. But if you think about discretization of energy levels and charge distribution as simultaneously satisfying a need to be close to the nucleus and far away from other electrons, you can start to get an idea of where electrons will want to situate themselves relative to a nucleus, and knowing that they can only exist at certain positions that correspond to certain energies. So a way to describe those energy levels is what we call quantum numbers. And yes, it does come out of quantum theory, and there's 4 of them. For each principal quantum number, you can have up to 5 second quantum numbers, and so on. There's certain numbers of them. And the higher the atomic number, the more you have of each. And there's a certain filling order that goes with them, which we'll go over. So N is typically referred to as the principal quantum number, L the second, which is also the orbital or probability distribution, and then the magnetic and spin refer to how they fill. And for each principal quantum number, you will have at least one s orbital, and quite often p's, and as you get into the higher atomic number, d's. So you can think also of your quantum levels and orbitals as places where electrons can exist. Whether or not there will be an electron there is dependent on the charge state of the atom. You can take electrons away or add them. So we will start filling those levels later as an exercise, but this is an energy versus principal quantum number map, just showing what the levels are. Again, if you've taken general chemistry, this is something you've seen before. But the first principal quantum number, which would represent a low energy state or a close proximity to the nucleus, you can only have that spherical s orbital. As you get to a higher energy, you get another s orbital, so this can be thought of as being nested effectively, going further away from the nucleus. You get another spherical charge distribution, and then you also have superimposed on that dumbbell charge distribution of the p orbitals. Third quantum number, going a very discretized step further away from the nucleus, you get a third spherical shell of charge distribution, a second set of p dumbbells. Taking a fourth step out, you get a fourth spherical shell, a third set of p orbital shaped, charge distribution shaped dumbbells, and then you pick up the d orbitals, which are yet another sort of dumbbell shape like we saw in the earlier slide. So you can think of advancement of principal quantum numbers as being effectively a set of increasing distance from the nucleus nested shells of these charge distributions that contain effectively a charge equal to 1 electron. If anyone remembers the Pauli exclusion principle, it's the way that you fill these energy levels, and again it goes on the idea that you want to, of course, fill the lowest energy state first, which is following from the rule of your negatively charged electrons wanting to be as close as possible to the nucleus. But you'll fill them in a certain way that has them be first all unpaired and then going back and being paired. And that satisfies a low energy state relative to electrons being proximate to one another. And so if we were to look at this element, which is sulfur, there's its full configuration, and also showing in spin up and spin down. That's the magnetic spin number, which just represents another energy state of electrons by themselves. And if anyone remembers, we would fill this with 1s with 1 electron spin up, followed by 1s with an electron spin down, 2s1, 2s2, 2p1, spin up, filling all 3 positions, go back and pair the spins up through 2p6, then we'd fill 3s1, 3s2, and then as you can see we have filled the 3p orbital positions all with spin up, and then there's 1 electron been added to spin down to make for a 3p4. So there are 2 orbitals in the 3rd principal quantum number, p orbitals, each only 1 electron, and they're staying as far away from each other as possible. There's 2 other ways of writing this configuration. One is called a valence configuration. The other is a shorthand that leverages the fact that sulfur is kind of built on top of neon. And this separates 2 fairly important concepts, and that's core and valence electrons. Core electrons are those that have principal quantum numbers less than the outermost or highest one. They're completely filled. They're very stable. They don't like to interact with anything because they're very stable. They're in their lowest energy state. There's not much that they have to gain in terms of lowering their energy by interacting with anything. They shield the nucleus very well from outlying outboard valence electrons. So other than determining the extent to which outboard valence electrons are or are not strongly attached to the nucleus, the core electrons don't have a lot to do with changing the nature of bonding and atomic material properties. Valence electrons, on the other hand, are in a very high energy state, first because they're farthest from the nucleus. They see the least amount of effective nuclear charge, and also because they are not in their most stable filled paired configuration, so which they would like to be. And so that lack of stability that comes from an unfilled state is truly the genesis of interatomic bonding and makes for, all condensed matter, liquids and solids that want to be in a bonded state. And that's bonded as a single element that would be in the solid state. So the neon that is in that shorthand configuration is effectively the first 2 quantum shells, 1s1, 2s2, 2p6. So that's all the filled shells, and then what makes sulfur is that 3rd principal quantum number in valence shell. Okay, a little bit more about valence versus core electrons. Valence electrons are those in unfilled shells. Filled shells are stable. Valence electrons are available for bonding because they are not in filled shells, and they tend to control chemical properties because they have a higher energy state and they can lower their energy state by interacting with the electrons of other materials. So here's another example of filled versus unfilled. You've got carbon, atomic number 6, 1s2, 2s2, 2s2, 2p2. And you can see in the red there, those are the valence electrons. Now, we have to talk about the full principal quantum number not being filled. Obviously, the s orbital of the second shell is filled, but the p orbitals are not. So when you talk about a valence shell, you're talking about the full principal quantum number not being satisfied for whatever it would want. And of course, the higher the principal quantum number, the more electrons it can accommodate, the more electrons it takes for it to be filled. 1 through 3, you only have s and p, so the most you can take is 8. As you get up into the higher quantum numbers, you have the d and f shells that take quite a few more electrons. D takes 10, for instance. Okay, so here's some examples of those. Again, stability of unfilled shells. Unfilled shells are in a higher energy state than filled. They reduce that energy by interacting with other electrons. It's a reduction in electrostatic energy, effectively. They can get to a lower energy state by banding together in a bond. And this just gives an example of filled versus unfilled, core versus valence electrons as we march up the periodic table. Hydrogen only has one shell, one orbital, and it only has one electron, and it's not filled. When you put another electron in it, you can get to helium, and that's a stable noble gas. Marching down the second or along the second row, same thing. We build on helium, we add a second principal quantum number, fill the s shell, fill the p shells. When we get the p shells of our second quantum number full, we're at neon, another stable noble gas. Notice noble gases have something in common. Non-reactive. They have all the electrons they need for the places that they can put them. They stand to gain nothing in terms of energy reduction by sharing electrons with anyone else. This is why they're so stable, why they're so non-reactive. It's why we use them for shielding and welding and things. They don't want to react, no matter how hot your substrate is. Very convenient. And so you see the same trend going down on the third row, starting with sodium. We now have a third principal quantum number, third shell, so to speak, opened up. We start dropping electrons in it. First we fill the s orbital, that spherical shell, then we start filling the p's. We get all the p orbitals of the third quantum number, the third shell full, and we have argon. Again, it is stable noble gas. And again, same trend with krypton, but of course needing a bit more in the way of electrons because now we are opening up the d shells of the third principal quantum number. You'll notice a bit of a reversal there, that we had a stable noble gas at argon filling the p orbitals of the third principal quantum number, or the third shell, but then we finished up with 3d10 going through 4p6 with krypton. And some of that is due to the fact over here that the d shells of the d orbitals of the third shell lie energetically between those spherical s orbitals of the fourth shell and the p orbitals of the fourth. And that's due to their shape. So there's, as you get up into the higher principal quantum numbers, higher shells, there's a lot more smearing and a lot more overlap in terms of exactly what is the most stable configuration for electrons. And that smearing, or the fact that you have that much energetic interlacing, you could put it here, you could put it there, it's very energetically similar. That leads to a richness of chemistry. It's one of the reasons that when we get those d shells in that third principal quantum number, we're starting into the transitional elements in the periodic table, and they have quite a few options for bonding. They have a lot of stable ionic states, stable valencies, a lot of chemical diversity. And that is where, in fact, many of our engineered materials, in the case of metals, come from, that first row transitional. And it's mainly due to those d shell electrons. Okay, flipping back here. And that, of course, leads us into periodic table trends, talking about the transitionals there in the middle. There are two very important trends that you can see when you look at a periodic table of elements. And if you're not familiar with the periodic table, there's quite a few web references, but effectively it is a guide to filling the principal quantum numbers, filling shells as you add protons in the nucleus and building up bigger and bigger atoms. And you read the table adding protons basically from left to right and from top to bottom. And each of those boxes, the top number within the box is the atomic number, so that's the number of protons. And then the position in the table tells you something about how many principal quantum numbers you have and which of the orbitals within that quantum number is how full. Generally, as you go from top to bottom, you are adding electrons in those spherical s orbital probability distributions. So you're adding spherical charge distributions, effectively nesting, like the nested wooden Russian dolls, one outside of another. And if you think about how well a spherical distribution of charge can shield something on the inside, it's very, very effective. So you're adding nest after nest after nest of these spherical charge distributions in the form of more and more S shells, each with an increasing principal quantum number as you go down the periodic table top to bottom. So hydrogen, lithium, sodium, potassium, rubidium, cesium, etc. That means that anything outboard of that nested bunch of spherical charge distributions is going to be very, very well shielded from the nucleus. It's not going to see much of that positive charge. So it's not going to have a lot of attractive force to the nucleus. So if you've got one lone electron sitting in an s orbital that's outboard of a whole lot of other s orbitals in inner principal quantum numbers and inner shells, it's going to have a very low attractive force to the nucleus. And that means it's easy to be captured by another atom that has higher electronegativity, that needs an electron to make a bond. That's the reason why the alkali metals, which is that first column in the periodic table, are very, very active. It's why sodium and potassium will ignite on contact with water and are often stored under oil. Lithium, not so much. Also reactive, but not as bad. The further down that column you go, the less tightly bound that outer electron is, and so the more reactive the element is in its metallic form. If you go the other way, if you stay at the same up-down level, but you move across the table, you're adding electrons effectively into the more dumbbell-shaped orbitals, but within the same shell, within that same principal quantum number. By arranging the electrons in anything other than a sphere and not generally placing them inboard of one another, you reduce their ability to shield one another. So the last electron to be added isn't necessarily being very well shielded from the nucleus by its fellow electrons within the same orbital. So it feels the nuclear pull pretty hard, and it really doesn't need to go anywhere. When it feels a strong pull from the nucleus, it's tightly bound. It's in a very low energy state, more like the core electrons. So as we move from left to right on the periodic table, our valence electrons are going to act a little bit more like core electrons, and the entire atom becomes less likely to lose an electron. Now, ultimately, when we get way over to the right, those electrons become so tightly bound that that atom can reach its low energy, full noble gas configuration quite easily by taking an electron from something else. You actually get an increase in reactivity, but this time in the other direction of wanting to gain an electron. But the trends basically still hold and are a function of how well the electrons shield one another. So in words, the valence electrons are shielded or screened from the positive electrostatic charge in the nucleus very well by core electrons, not so well by other valence electrons. So the screening effectiveness of any electron on any other electron depends on how deep they are relative to one another. So an electron that is inboard or closer to the nucleus in a lower shell will screen an outboard electron better than an electron that's in the same shell. And s orbitals screen better than anything else because of their spherical distribution. When you add a principal quantum number, you add a shell, you go from 1 to 2 to 3, you are by definition adding s orbitals. So you're adding those best screening electrons. And that's another reason why as you jump down the table, you're jumping quantum numbers, you're adding more of these spherical distributions, so you get great shielding. So we can quantify this, at least a little bit, in terms of effective nuclear charge, and that's Z effective. So that's charge from the nucleus. And you can think about it in terms of a positive charge, Z, coming from the nucleus, which goes up by 1 every time we increase atomic number by 1. So if you look down the difference between sodium, magnesium, and aluminum, we're moving across the periodic table. So sodium has an atomic number of 11. You add a proton, you get magnesium at 12. You add a proton, you get aluminum at 3. So the actual nuclear charge going from sodium to aluminum went up by 2. The effective nuclear charge didn't go up by the same amount. It went up by something less, even though we were adding 1 electron every time we added a proton, because we're making atoms, not ions. We're having to add an electron every time we add a proton. Each electron we added didn't screen that full single unit positive charge as well as the one before. And so Z effective went up because S went down. So that's the across trend. And if you think about the reactivity of sodium versus magnesium versus aluminum, although they are all active metals, they will all burn in air given enough provocation. It takes far less provocation to get sodium to ignite. In fact, if you expose it to water, it will happily give up electrons in order to liberate some hydrogen and can actually burst into flames, which is very dramatic but not recommended outside of a controlled laboratory experiment. Aluminum, on the other hand, is active enough to form an oxide film that shuts down further reaction but does not generally ignite in air unless it's given a lot of activation energy and surface area. Okay, so same trend holds going down except in the opposite direction. Lithium to potassium, we've added a lot of extra true nuclear charge. So we've gone up by 16 charge units, positive charge units, lithium to potassium. But the effective nuclear charge that those last few electrons see is very small, because we have, every time we jumping from lithium, sodium to potassium, we've added 2 big spherical electronic negative charge distributions. So electron number 19, that 4s1, is only loosely associated with the nucleus, and hence potassium is very, very reactive. Okay, so we can use Coulombic ideas also to think in terms of the difference between spatial distribution and shielding charge to get an idea of attractive and repulsive forces within atoms. And this is where we're gonna cheat a little bit and step back from the idea of a charge distribution, which is the way electrons really are distributed around the nucleus, to thinking about point charges. We should not be thinking about electrons around an atom as point charges, but for this exercise we can think about it as point charges and use Coulomb's law, which this is a variant of, where the attractive or repulsive force between charged particles there, being proportional to the magnitude of the 2 charges divided by the square of the distance between. So if you think about adding quantum numbers, you're separating an electron in that outer shell from the nucleus. That would be equivalent to increasing the distance. So you can see if you increase the distance by 2 over on the left-hand side of a +6 charge versus a -1, simulating a nucleus and a single electron out there somewhere in some outer shell. If we double the radius, we reduce the interparticle force by a factor of 4. So it's 0.25 times the force in the A1 case there. And likewise, if we kept that radius the same, but we added a bunch of inboard charges, which is shown there by the yellow dashed lines, instead of having 3 negative charges outboard of your +6 in the middle there, you added another 2 in another shell, and then you looked at the effective attractive or repulsive forces. You can see that that attractive force went down by a factor of 3. So that's kind of a thought experiment way of envisioning the effect of effective nuclear charge and screening electrons in an atom. But caution, they are not point charges in an atom. We will use this much more correctly and effectively when we start looking at the effect of interionic attractive and repulsive forces, and we build up an ionic crystal, which will be something that you can do as an exercise using Coulomb's law, and is done in a lot of classes. So, what properties track with effective nuclear force? So these are the foundations of what will become interatomic forces and the basis of chemical bonding. And they are all effectively related to one another. So the first one that tracks is electronegativity, which is a tendency to acquire electrons in order to complete that valence shell filling and reach a stable configuration. This is an arbitrary number, ranges from 0.7 to 4, higher numbers being more likely to want to withdraw electrons from something else. So fluorine's out near 4, sodium, potassium, rubidium would be down closer to 0.7. So the higher the effective nuclear force, higher the electronegativity. First, ionization energy. That's the energy required to completely remove one electron. This is important when you do some types of spectroscopy, when you probe the core electron structure to determine with an electron beam or with an X-ray beam, and to try to determine what type of element you have. You'll knock a valence electron out. It's obviously easier to knock that out if it's not very tightly bound. So the first ionization energy will be higher with higher effective nuclear force. Atomic radius goes the other way. Atomic radius will increase with the number of shells, which means increasing with the number of S-shaped orbitals, those spherical orbitals, and the more we have of those, the less tightly we have things bound. So the higher the effective nuclear force, typically the lower the atomic radius. Things are held tighter, they're held closer. And again, electron affinity is related to electronegativity. It's a more general term for wanting electrons. It's not quantified on a scale. So here's a graphic of periodic table trends. If you are looking to make a bond, or you want some idea of what an ionic or a covalent compound is going to do, or how you would react something, maybe you're trying to decide if a compound would be stable, these are some general trends to look for. So you're going to tend to get things going in these directions. Things will be more tightly bound. You'll have higher ionization energy, higher electron affinity as you go from left to right, opposite going from down to up. Metallic character and non-metallic character in terms of the periodic table typically refers to reactivity, willingness to lose an electron. It does not in this case mean metallic bonding, although many more of the metallic character elements end up forming metallic bonds, and there is some advantage to sharing those electrons. Okay, special periodic groups. These are names for different portions of the periodic table that have very common characteristics, and again, these characteristics are arising mainly from that effective nuclear charge and the trends that you saw earlier. By definition, the first column over on the left-hand side, they're known as alkali metals. They always have a valency of +1. They will lose one electron only. They only have one electron in their valence shell to lose. They are the most electropositive, the most likely to give up an electron, the lowest effective nuclear force. The next one over, the column 2A, are called alkali earths. They are also very electropositive, but not as electropositive as the alkali metals. They only have 2 electrons in their valence shell. They can only lose 2. They'll only achieve a valency of +2. So these will form compounds like magnesium oxide, calcium oxide. Over the alkali metals will form salts like sodium chloride and whatnot. The 3B through 2B are the transitional metals. This is where we start to fill D and F orbitals across various principal quantum shells. And they can have valencies of anything from soup to nuts. Typically 2, 3, and 6 are the most common ones, although the ones in the middle, especially things like molybdenum, have several more. They're moderately electropositive. Some, like titanium, are much more active, so they're more electropositive. Obviously, we have some of the most noble metals in there, like platinum and gold, that are fairly noble and don't want to give up electrons, so there's quite a range. When we pass through the transitional metals, we're again filling up our p shells for whatever given principal quantum number, and as you cross from 2b to 3a, that portion of the periodic table is typically called nonmetallics or semi-metals down near the bottom. And as you reach the last row before the stable noble gases, 7a, these are the most electronegative elements. They're called the halogens, and they tend to form stable salts, sodium chloride, sodium fluoride. They are also some of the most corrosive compounds. They like to take electrons from other things. And of course, column 0 are the noble gases. So you'll hear the terms alkali metal, alkali earth, transitions, and halogens as you go through your career. Okay, we're going to pause this lecture before we dive into chemical bonding and resume with lecture number 3. I hope you've enjoyed filling up shells and understanding how the structure of atoms and its electron filling sets us up for chemical bonding. And we'll get into a little quantification of bond energy and bond strength using some force equilibrium and Coulomb's law, and then see how that leads us into characters of chemical bonds that we'll need to use for materials. See you next time.